Hey everyone. So in today's quick revision video for A2 chemistry, we're going to be talking about the equilibria. So before we talk about equilibria, there's first thing that we need to understand from AS level concept is the definition for acids and base. Acid is a hydrogen ion donor and base is anything which is a hydrogen ion acceptor. Then we should have we have few definitions and their terminology. First is Kw. Now, Kw, basically also known as the self-dissociation constant of water or self-ionization constant for water, is basically the product of the hydrogen ion concentration and OH minus ion concentration at equilibria in distilled water. Obviously, at 298 Kelvin and 101 kilopascal, this value is actually equal to 1.00 exponent minus 14 mole square dm minus 6. But as the temperature changes, this value also changes. We should understand that as the temperature increases, the value for Kw also increases, which means the pH and the pOH of distilled water decrease. Do not say directly proportional and inversely proportional, but I would rather say that with higher temperature, more dissociation happens, so more ions are produced of each kind, so Kw increases and ultimately pH and pOH decrease. Ka is known as the acid dissociation constant, which is basically hydrogen ion and conjugate base ion concentration divided by the unionized acid. pK is basically the power of the Ka, or you can say the negative log of Ka, and pH, like we all know, is the negative log of hydrogen ion concentration. A buffer is any substance which will resist changes in pH when a small amount of acid and alkali are added. This definition is from the syllabus and I would recommend memorizing this definition. In order to make a buffer, you take a strong alkali and you take excess weak acid and you add some small amount of strong alkali so that a part of weak acid is neutralized and some part of acid is still there. So it becomes a combination of weak acid and conjugate base. Another possibility is you take weak acid, you add it into excess alkali like vice versa, and even then you get some amount of weak acid with some amount of conjugate base. You do this also with weak base instead of weak acid, but obviously then you'll take the other counteracting chemical. In order to find the pH of buffer solutions, we have this equation 9, which is pH is equal to pKa plus log conjugate base ion concentration divided by the weak acid concentration. I have solved a big question of buffers in my Equilibria A2 level chemistry playlist, so do give it a watch and see if it's making sense to you guys. Then we have solubility product, which works for sparingly soluble salts in water. If we talk about solubility product, it is basically when a salt is in equilibrium with its own ions which are dissolved in aqueous state. In order to find the KSP, we take the product of the ion concentration at equilibrium in a saturated solution. Always remember, we do not divide the ion concentration by anything, because in KSP, the ion concentration, the cation concentration and the anion concentration at a saturated solution is taken into account and you take a product of it. Make sure nothing is in denominator. If you have a different kind of dissociation, for example XY2, where X has a positive 2 ion and Y is a minus 1 ion, then KSP can also be written as X2 ion, like X2 plus, and Y minus 1 with a square, because obviously that is the mole ratio, as you can see in this equation over here. Now, what's solubility? How we can find solubility from KSP? So from KSP, we can find solubility for these kind of equilibria like this. And if it's a simple equilibrium, you can find the solubility like this. It's very simple, right? Now moving on, what's partition coefficient? Partition coefficient is basically the ratio of the concentrations of a solute into immiscible solvents at equilibrium. I've also highlighted the keywords that you should mention within your answer. Basically, when we talk about partition coefficient, we have this understanding of you can say single extraction, double extraction, what actually we do over there is that we have a solvent. For example, we have a solvent which has a higher density, the black solvent, and it has 1 gram of A dissolved in it. Now suddenly we put 100 centimeter cube of the other solvent on top of A, and now we have two immiscible solvents. Some of the A is gonna be moving from the bottom layer towards the topper layer, and then as a result there's gonna be an equilibrium established. In original layer we had 1 gram of X, but now it won't be 1 gram, it's gonna be 1 minus X gram, because some amount is gonna be moving towards the layer at the top. How much is moving to the layer at the top? X gram. So Kpc becomes X gram over 100 because it has to be a concentration, right? So X gram divided by 100 centimeter cube divided by 1 minus X gram over 100 centimeter cube. Why are we not converting into decimeter cube? Why are we not finding the moles instead of just we are using grams? Because it's going to be a ratio. For a ratio, you don't have to convert both volumes into decimeter cube. You can work with cm cube also. So this was all about equilibria. Stay tuned, guys. Thanks.